Welcome to part 3. I originally had recorded this yesterday, actually. It's when I had recorded the other 2 videos. I was thinking actually it was Monday, so it's been kind of 2 days. Everything's blurring together now that the school week has started here for 2026. And I had recorded, but my phone ran out of memory, so I had to redo this video because it quit filming and I didn't realize it. Which is always a blast because I felt like it went really good. So we'll see if the second go around is any better or it's probably just going to be worse. So sorry. But what I kind of promised in this one is we were going to focus on vector operations, specifically looking at addition, subtraction, and scaling, and what happens with those graphically speaking. And so we saw the algebra, and intuitively we can kind of see how we combine these things, but I think it's through the visual representation for specifically 2-dimensional vectors because they're easier to kind of see on a 2D plane. Exactly how, when we add them, we work with like components and why that makes sense in terms of how we add. And then there's some really interesting relationships, geometric shapes that get involved, in particular when we talk about subtraction and what that means as well. But it all starts with vector addition, and so before we even get to that point, I also apologize, I've got 2 vectors, I'm not working on a grid, so I'm going to try to make this as to scale as I can, but if you are in the online class, my notes, I have graph paper, it's gridded, and that's, you can actually see a little bit cleaner, and it kind of verifies more of why the addition works the way it works, and so I'd definitely highly encourage if you're to follow along with the notes, but to look at those and compare. And this is more just kind of a visual talking to back up my very poorly written scribbles in the notes. And so when we are looking at a vector, just to kind of do a quick review, vector u has components 2 and 3. And so if I am sketching that vector in standard position, this is saying my initial point is at the origin 0, 0. I'm taking 2 steps to the right and 3 steps vertically to get to my terminal point. And so because we're placing this in standard position, you'll see I kind of use the parentheses, and we'll talk more at the end of this video about what is the difference between a point and a vector. Because you can either use notation like this when we're talking about standard and we're starting at the origin, or you may see a more exaggerated vector notation like this. And this notation is a lot more helpful if your vector is placed anywhere on an open grid and not necessarily being placed with a starting point at the origin. We're just trying to compare vectors themselves, I guess might be the best way to kind of to reference it. Now vector v, same thing, I've got 4 steps to the right as my horizontal component, 1 step up. Notice this one is a little bit flatter of a vector, and here's vector v. And what I want to do with these 2 vectors is to go through and combine them. I'd like to add them and create a new vector, which I'm going to refer to as w, where I am specifically going to say u plus v. And graphically speaking, when I'm adding 2 vectors together, in particular if you haven't taken physics or seen this before, or it's been a while, is we add vectors head to tail method is the technique that we want to do. And to kind of help illustrate what that means in terms of head-to-tail method is, again, thinking about vectors as directions for how to move from some initial point to some new terminal point. And the resultant vector, which is w, would be that straight line path from our original initial to that new terminal point that we have. A vector is always that straight path. So although we may be walking 2 paths to get to a certain location, the answer is that final vector that we can draw. And I'm going to try to represent that, try to color coordinate it, make it look all pretty, but we'll kind of see. So I'm going to resketch in kind of a new grid here instead of trying to overlap everything. And again, doing this to scale as best I can. I'm going to try to mark these tick marks. We got 1, 2, 3, 4, 5, one more making 6. 1, 2, 3, 4, 5, going up. 1, 2, 3, 4, 5, going here. And so if I think about, I want to create the resultant vector w by walking u and then walking v, thinking about the plus sign as the word and, I can look at u as a certain amount of steps in terms of walking. So again, think about how we sketched this. We said to the right 2 units because that was my horizontal component, and then up 3. And if I then want to walk V, if I follow this steps, I'm going to go right 4 and then up 1. So if I do this, and I start with U, and I say, okay, well, I'm going to go 2 to the right and 3 up, 1, 2, 3. Here's my vector of U kind of replicated over here. And then from this point, I'm now going to walk V. I'm going to go 4 more steps to the right. So 1, 2, 3, 4, the 6 in anticipation. And then go 1 more step up, so I'm placed here. And so if I draw V, and I attach it head to tail method, my answer for W would be the straight line going from here to here. I apologize, this red is kind of blurry, so hopefully it kind of shows up okay. This red line would represent W. That's my resultant vector. And if I was to think about what the components for W would be, we can kind of see it on the graph. I would have a horizontal component of 6, which this is my overall, and a vertical component of 4. And that's really, really important to notice and kind of think about, because if we're adding, and what we talked about with the algebra, is that if I just add my like components, it's going to create that resultant vector. And notice that's what we would get. 2 and 4 give me 6, 3 and 1 give me 4. We have our final resultant vector. And so this is how we work graphically. This is what you see again in physics. We can kind of create these shapes here. And a little, not necessarily more important, but one of the big connections that I want you to kind of notice here is that, again, how we move horizontally is only affected by how we move horizontally. So like the 6 in the answer means I'm moving 2 and then I'm moving 4, but it doesn't matter the order that we were to do that in. If I go 4 and then I go 2, we still end up at 6. It's the same thing in terms of my vertical components. The vertical components are only affected by vertical components. So if I was to go up 3 and then go up 1, that's the exact same thing as going up 1 and then going up 3 in this context. And so I walked U and then I walked V, but we didn't necessarily have to do it in that order. I could have gone V and said, okay, 1, 2, 3, 4, 1. So here's my vector V, and then walk U. So if I draw that, notice how it kind of creates this parallel lines. We create a parallelogram. This is where I'm going to totally butcher spelling, so I apologize. Don't spell check me. But we create a parallelogram. And notice that my resultant vector, when I'm adding these two together, the answer is the main diagonal here from this corner to this corner. And that represents, and that's always going to be true when I'm adding two vectors like that in two-dimensional space. And this picture is, there's going to be an interesting connection with that as we kind of continue building what the operations are and how we can see them and represent them. And so this is how vector addition works, graphically speaking. Hopefully it kind of gives a little bit more background as to why we add like components. You can kind of see the connection there, why it makes it so intuitive when I'm really looking at it. The second operation that we want to look at, and there's three total that we'll talk about in this video, is scaling. And one of the better ways to kind of think about scaling, grab the eraser, is scaling is multiplying a vector by a scalar, by a single number. Remember, we kind of referenced geometry in that we are taking a shape and I'm dilating it. I don't necessarily want to change its direction. I just want to make the length greater or shorter. So if my arrow is pointing this way, so I guess in reference northeast, I want to maintain that direction of northeast, but I might just want to enlarge the arrow. And again, remember, this is what's referred to as scaling. And so for example, let's say I want to take my vector of u and I want to double it. So I want to scale it by 2. And if we scale, multiplication like this is just repeated addition. So when I say 2u, I'm really looking at this as u and then travel u again. In other words, scalars can be represented through vector addition. That's why we start with vector addition and build off of it. And so if I think about u as saying 2 to the right, 3 up, then 2u would say to do this again. I'm going to go another 2 steps to the right, and then I'm going to go another 3 steps up. I'm going to put my point, and then again, stretch this new line, sketch, stretch, whatever. And so I have 2 u's that are now added together, and my final answer would be the overall arrow going from my initial point to my terminal point. Well, observe that this terminal point is 4, 6. it is double what u was. So this answer of 4 comma 6 is just 2 times 2, 3. Working with scalars, it works very intuitively. It's this idea of distributing, even though it's not really the distributive property, but the idea kind of holds. Whatever I'm multiplying in terms of my number here with a vector, we can multiply the components of that vector. Even matrices, which I'm going to film a little bit after this, if I'm multiplying a matrix by a scalar, that scalar distributes and multiplies all of the entries. Again, a very intuitive notion here, but very, very important to observe. So 2u would be the overall arrow represented if I was to sketch it from here to here. And now that's scaling. Again, it makes sense. Now, at the core, scaling does not change the direction. So if I'm multiplying by a positive scalar, very, very key, positive, real number, my vector will not change its direction. But it is possible to change the direction of a vector by multiplying by a scalar. And to showcase that, what I'm going to do is take my vector for u, and I'm going to multiply it in the most simplest case by -1. So I'm going to say, okay, let's take -1 and let's multiply that with u. And we've discussed how when I do this, we're just multiplying the components. So if the components are 2, 3, the new vector is -2, -3. This would multiply each piece. And the connection that I want to make, graphically speaking, to kind of show you what's happening with this, is that instead of taking 2 steps to the right and 3 steps up, we're now just doing the reverse or the opposite of those steps. I'm going to take 2 steps to the left and 3 steps down. I'm going to end up with a vector now going here, and a very poorly drawn, again, that's why I would reference the notes in the grid, that this would stay in the same line, but the direction is now 180 degrees. And you can kind of think about this in any way, but multiplying a vector by a negative is just going to take something that may be facing in this direction, and instead of walking forwards, we're now going to essentially be walking backwards. Still staying along the same path, still staying along that main original angle, but again, now going 180 degrees. If you had just gotten out of working with polar coordinates are very, very similar. I have a theta, and then I have a r, and if r is negative, instead of measuring, say, pi over 4 and then walking out a certain radius, I would then walk backwards from pi over 4, and this causes, multiple equivalent points and expressions, and it's very, 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 very similar with vectors. But the important aspect of this that I wanted to take from multiplying with negatives is that this is essentially a 2-step process. The negative is what changes the direction. The 1 is what changes the magnitude. It changes the length. So if I was to take a vector like this and say, instead of -1, multiply it by -2, it's not this entire thing that is flipping. It's just a negative. The negative is what flips the direction to be 180. The 2 then stretches that vector. And so you can kind of look at this as 2 operations or 2 things happening that most people just tend to do at once. And so you can kind of get lost in the fact that this is kind of 2 separate transformations that we're applying to the vector itself. And so just something to kind of keep in your back pocket. Now, the reason why negatives, and we talk about the scaling next, is that between these 2 operations, this unlocks kind of everything. And what we'll see with linear algebra in particular is that linear algebra is specifically defined using 2 primary operations. We have addition and we have scalar multiplication. And everything is built off of those 2 things. We'll see this later, so I won't dig too much into it now. But everything at its core follows with those. Now, what can help us is, now that we can deal with negatives like this, if I wanted to subtract my 2 vectors, so if I was to draw out and say, okay, I want a new resultant vector, but I want to do v minus u. So I want to subtract in this order. You'll kind of see why I chose this order. Subtraction is addition. It's the inverse, right? And so when I look at subtraction, it's formally defined as plus a negative. And this is the key. When I'm subtracting vectors, we're not really subtracting vectors. We're still adding. What we're doing is we're adding the 180 degrees. We're adding the reflection of the vector itself. And so when I do this, intuitively, you don't really ever distribute the negative throughout and combine them. I can just look at it and say, okay, well, 4 minus 2, because at its core, that's what's really happening. But I want to show you again geometrically what this would look like. And so I'm going to sketch, again, our scenario. I've got 1, 2, 3, 4, 1. There's my V. And then remember that I'm adding to this negative u. So instead of going 2 to the right and 3 up, I'm going negative 2 to the left, and I'm going 3 down. So negative 3 on my components. So from here, I'm going again 1, 2 steps to the left, and then 3 steps down. 1, 2, 3, placing me here. So when I add negative u to it, and again, this is a very poorly drawn to scale, so don't worry too much about the scale here. P would be the vector that's sketched from the origin to here. This would be my resultant P from doing the subtraction. And this vector, if I want to go through and find its components, we can see is 2 to the right, it's my horizontal, and 2 down. Again, 4 minus 2, 1 minus 3. And what I want you to notice now, in terms of a connection from what we were looking at earlier, is that this vector, 2, negative 2, if I move it from the origin, but I maintain the vector, so vector P is still 2 to the right and 2 down, notice from this corner to this corner, I am 1, 2 to the right, and I'm 1, 2 down. In other words, if I place P here, the subtraction of the two vectors, V and U, form the other diagonal of that parallelogram. And it's why you see so often when working with vectors this parallelogram conjecture and theory and fact. I don't really know if it's a theorem or not off the top of my head. I guess you might be able to call it postulate. This is where I apologize for the informal in the background, but it's just kind of an interesting relationship between the addition of vectors and the subtraction of vectors, specifically when we approach it from a geometric perspective. And when you're looking at this, then a question can kind of arise that I'll leave as a challenge, and I kind of mentioned it in the notes. If you, again, are looking at the notes, you can kind of see the question I ask, or what I kind of pose after this, is that, well, is that only because of the order, right? I mentioned from the very beginning that I'm choosing to do V minus U. Well, what if I did U minus V? What's interesting is swapping the order just swaps the direction of how we travel between the 2 points. Instead of P going from 2 to the right, 2 down, it's taking the 180. We're going 2 up and 2 to the left. Notice how you're changing the negative, you're changing the direction. And so there's some really interesting behaviors that happen between all of it. And so operations on vectors kind of falls under these two categories, addition and scaling. Notice subtraction is even still addition. We will look in terms of matrix operations in the next lesson, like how do matrices interact, how do vectors interact with one another in terms of multiplication. We've seen dot products and things like that before. And then as we continue into linear algebra, we'll see how vectors interact more with one another, cross products, dot products, etc., inner products, all that fun stuff. Last thing I guess I want to leave you with is just a quick discussion again on notation of points versus vectors. When I list a vector like this, saying 2, 3, if this vector goes through or starts at the origin, then remember that the terminal point and the components are the same, so this notation is appropriate. But in this kind of case, like if I want to talk about this vector P, but I don't want to think about it in terms of a Cartesian system, and I want to think about this vector here, this vector and this vector are only equivalent when I'm looking at it in terms of its vector components, like this. If I wanted to list it as its array and say 2, -2, these two vectors would be the same. But if I want to consider where the vector is placed in space, then we have to be a little bit more specific, and I can't just use this notation, or I just can't use this notation. We have to take into account where my vector is starting. And so we're going to always kind of keep it a little bit simpler. In linear algebra, our starting point, essentially we're always looking at the origin. We need to pass through the origin or the zero vector. We'll talk more about that a little bit later. The follow-up and kind of last thing that I want to hit on is this word called basis. And my goal is just to really kind of outline very quickly the connection between a basis in these vectors these points, this kind of conversation that we're having around when are two vectors the same and all of that kind of stuff. And it really boils down to what system are we graphing in. So when I talk about the Cartesian coordinate system, the Cartesian plane, specifically in R2, we're looking at our standard x and y axis. And in this class, we'll talk about what if I want to change this, what if I don't want it to be rectangular, and I'm not really talking about changing it to be polar, but what if I wanted this to be skewed? And we'll talk about how we can transform and look at all that. But when I'm looking at this Cartesian plane, if I'm looking at the real numbers, the two-dimensional space, there's an infinite number of locations here on this board. And if I want to talk about the vectors that can get me to any point on this board, there's a way that we can do that in terms of linear combinations. So by talking about and using addition and scaling, we can talk about what are the most basic vectors that we can use to get us anywhere in a plane, on a grid, on a graph, whether that's two-dimensional space, three-dimensional space, or even going above that. And again, geometrically speaking, this is a little bit cleaner. And so the way that we can do that is something that we talked about before, that if you recall from the previous videos, or even your work in multivariable or something else, I have the unit vector I, which is the vector 1, 0. This creates any movement horizontal. And then I have my unit vector j, which accounts for any vertical motion. And so if I take these two vectors and I combine them together, if I say I plus j, this will give me any coordinate essentially along the circle, almost a unit circle in a way. It's everything, essentially in this case, just not even a circle, sorry. It's really just a single point where I'm going one step to the right and one step up. So it's describing that point there. But if I want to describe any point along this diagonal, then I need to rescale this by multiplying it by certain values. And so what I can do here is then take these vectors and multiply them by scalars a and b. And if I do that, now I can shift and say maybe I'm going all the way out here and then I'm going up here giving me this point. Maybe I want to find a location for this one. Well, what's the multiplier to go here and multiplier to go here? Here's the vector that gets me there. In other words, this linear combination forms a way to get every point in the Cartesian plane using just these two vectors and scalar multiples of just these two vectors. And so what we're describing then is the basis for the R2 plane. Everything in this plane can be formed using the basis or the base vectors 1, 0, and 0, 1. And so when we talk about basis, that's what we're talking about. What are the vectors that are necessary to combine in any fashion that we want to get us every possible point or location in a certain amount of space? And so that's what a basis is. And so this is something that's we're going to be talking about a lot and have a lot of conversations around and some of the work that we'll see in terms of spaces and things like that. So that rounds us out for vectors. In the next set of videos, we're going to review some matrix operations. What the hell is a matrix? A lot of people haven't seen that as much. If, again, you took multivariable, you've had some exposure to matrices, but it's not what we need in terms of foundation. It's not enough. A lot of people think, I've seen it, I'm great, but you haven't really worked with adding or subtracting, multiplying with vectors and that kind of stuff. So that's what we're going to look at next. It's the one that I would encourage if you're more comfortable with vectors. And as always, we'll have some practice problems that you can look at if you're in the online class. Thank you.